Welcome to the session on simple cases in fluid flow as part of the NPTEL MOOC on transport phenomena in materials. In this session, we will be looking at simple cases where the problem can be reduced to one diffusion term on the right hand side of the Navier-Stokes equation, and so that the analytical solutions are very easy for us to see with just a couple of steps of integration. We will be sticking to the rectangular coordinate system in this session. So, the cases that we are looking at are as follows. So, we will take a very trivial case where we will get the Newton's law back, which we have put in at the stage where the constitutive equation is required, and we will then take couple of problems which are very popular in the metallurgical and materials curricula, namely the film flow on inclined plane, flow between two plates, and the mixing film flow. So, here is the first case. So, here is a trivial case reproducing the Newton's law. So, the situation is as follows: we have got liquid between two parallel rigid plates, and the top plate is then moved at a velocity u1 max, and because of the motion the liquid is sticking to the top plate. So, we have got basically the fluid moving in the right hand side direction, that is in the x1 direction. So, the fluid flow is only due to the motion of the top wall, and there is no other term that is active. In other words, there is no pressure drop we are talking about, there is no body force we are talking about, and the boundary conditions are as follows. At the top wall we have got no slip condition with a moving wall. So, the velocity at the top surface would be the same as that of the wall, and at the bottom we have got no slip condition for a stationary wall, then you have got the velocity equal to 0 at the bottom. So, in this case then what we always do for many of these problems is as follows. We start with the Navier-Stokes equation for the velocity component that is relevant. So, we always write the full equation so that we are conscious of all the terms, and then we start striking out the terms as we do not need them later on. Okay. So, u1 is the component that is relevant. So, that is what is written here. So, the equation is already assuming that it is a Newtonian fluid, it is an incompressible fluid, and it has constant viscosity. So, the top three assumptions are already made, and so we are going to make some more assumptions which will reduce this equation to an extremely simple form. So, first assumption here is a steady state. So, which means that we can strike off this term because of the assumption number 4, and unidirectional velocity along x1 direction, which we mean by saying that u2 and u3 are 0. So, which means that we got this term and this term being dropped off because of the assumption number 5. And then we also say that in these situations the velocity variation of u1 can be along the x2 or x3 direction. So, we choose that it is varying only along the x2 direction. So, which means that the variation of u1 along the x3 direction can be dropped. Okay, that is because of the assumption number 6. Okay, and then we say that the fluid flow is well developed along the x1 direction. So, which means that dou u1 by dou x1 is 0. So, we drop this term because of this assumption 7, and also this term goes away, is the second derivative of the same term. So, this one also goes away, and then we say that there is no body force or pressure drop in this particular problem. It is a very simple problem. So, we basically knock off these two terms also because of the assumption 8. So, which leaves us with only one term here, okay, and that is equal to 0, and therefore, the equation appears in the simple form as written here, okay, and you can immediately see that the solution should be a straight line, and that is what is the solution that is given here. Okay, when we integrate this twice we get ax2 plus b, and the integration constants are to be found from the boundary conditions which we have already mentioned. So, at the top wall the x2 is equal to delta value, you have got velocity equal to u1 maximum, at the bottom it is 0. So, when you substitute you get the functional form for the velocity, which is basically proportional to the distance in the y direction, and scaling of the maximum velocity with the factor delta that is at the denominator. So, this is a solution which gives you a straight line profile, which is the simplest profile that is possible for any solution of Navier-Stokes equation. Okay. So, we see this plot, the plot actually shows you that it is a straight line. So, here I am marking the profile of the velocity u1, okay, as a function of x2 or y. Okay. So, which means if you want to show this on the schematic itself, then you could also do that. So, you could do that here in this manner. The axis can be drawn, okay, and then this is x2 and this is u1, and then we show what is the maximum velocity there, and the velocity would look like that, okay, which means that as you go up in the thickness of the layer, the velocity is picking up to a maximum value given by this term, okay. And we can also see that the Newton's law we have retrieved, because when we now see that the shear stress is calculated as per the same formula, then it comes out to be a constant, and we can see that here it comes as a constant because u1 is constant and delta is in the denominator, and u1 is positive because it is along the direction of x1. So, which means that tau 21 is positive and it is constant. So, that is why the plot of tau with respect to x2 is just a constant line, vertical line, that is going like this. So, which actually means that what does it mean when we say tau is positive? Okay. Of course, when we substitute any value of x or y, if it is a functional form, and then see that it goes to negative or positive, there must be a meaning for that. So, for that we introduce the convention by which we define how the value of tau should be interpreted. The convention is different from the book Bird, Lightfoot, Stewart. We take the so called positive convention here, and it is as follows. So, this definition will be repeated every problem in this session, so that we can commit it to our memory. The shear stress tau is basically the stress exerted on a plane y. You can see that tau is written as this. So, tau yx. So, we just this and this. Okay. So, one of them is plane and another is the direction. Of course, so one of the plane and another is direction, we can swap them because of the symmetry. So, the tau exerted on a plane y is in the direction positive direction x, and it is exerted by the layer at a greater y on the layer at a lesser y. So, if that is the case, then the shear stress is positive. In case it is the other way, then it becomes negative. Okay. So, this is the convention by which the mathematical way it comes out when we substitute different values of x or y as the case may be, it will all come to be the same convention, because we are using the same expression for the Newton's law. Okay. So, in this case, when you take the plane x2 equal to 0, so you would see that, so you see here this plane is here, it is shown here in this orange line. So, if you take that plane, for example, at a greater y, that is at a higher value of x2. So, here this is the higher value, that is liquid, okay, and the lower value of y is basically the wall. Okay. So, the force or the stress that is exerted by the liquid on wall, if it is in the positive x direction, then the stress is positive, which is actually true. The reason is that the top wall is moved along the x direction, and therefore, the liquid is flowing in this manner, and therefore, liquid is trying to move in the plus x direction. The stationary wall is trying to stop it. So, the wall is exerting a stress in this manner, the liquid is exerting in that manner, and therefore, the tau that you get at the value x2 is equal to 0 would then be deemed as positive. That is what we have also got from the mathematical expression. Okay. So, we check this kind of a convention even in other coordinate systems, and very useful to remember this convention to apply in other situations also. So, we now go to another problem which is quite popular, and this is also from the industrial application, because when we want to transfer some liquid metal or slag from one place to another place, then you may have inclined planes where the liquid would flow, and usually the liquid is then exposed to the atmosphere. So, you have got here gaseous atmosphere, and what would happen to the top surface? Would there be a pickup of oxygen or release of hydrogen, etc.? These are all issues of concern for a metallurgist. So, you have got here basically a wall which is stationary, and then the liquid is exposed to the gas. So, if this is the problem, then how do we arrive at a functional form for the velocity as a function of distance? So, we choose that the coordinate system, so that the velocity is a single component. So, we see that velocity should be only along the x1 direction. So, the flow is basically u1, and it should be a function of x2. So, this way we choose, so that the problem is simplified. The driving force, so reason why the flow is happening is because of the body force term, that is g cos theta along this direction. So, if you take the component in this direction, so you have got g cos theta, and that is the body force that is acting, okay, because of which the flow is taking place. And the boundary conditions, as we discussed in the previous session, are as follows. On the bottom surface you have got a stationary wall, so the liquid does not move relative to that. So, the no slip condition would come of use, which means that this velocity is 0 at the bottom wall. And at the top you have got the liquid layer in contact with the gas. The gas has very less density, so it cannot withstand any stress on the surface. So, the free surface you will have the stress is 0, and which means that according to the Newton's law, mu times dou u by dou y is 0, which means that the slope of the velocity with respect to the y direction is 0 at the top surface. So, we have got the boundary conditions, and we have got the reason why the fluid flow is taking place. So, we then can start the solution by writing the Navier-Stokes equation with the component for the component u1. Okay. So, here we have the same situation, we have got the equation written already for these 3 assumptions. So, these are already done, because of which the equation appears in that form, and we assume that this flow is taking place for a long time and at a steady state. So, we knock off the first term because of the assumption 4, and we say that the velocity is only along x1. So, x2 and x3 directions there is no velocity, which means that u2 is equal to u3 is equal to 0. So, which means that I can remove these 2 terms according to the assumption 5. Okay. And then the velocity variation can also be chosen along either x2 or x3. So, in the depth direction of the plane we do not want to look at any variation. So, we would like to knock off this term. So, there is no variation along x3 direction. And then we say that the velocity profile is fully developed, that is, as the liquid is falling down the plane it does not accelerate, which actually is not true actually if the plate is quite long, but we may make the problem simpler by assuming this. So, we knock off this term from the assumption 7, and the second derivative of this term will also be vanishing. So, that should go away. And we also say, in addition to the assumptions that we have listed till now, there is no pressure drop. So, this will be going away because of this. So, which means that now our equation has reduced to having only 2 terms. So, we have got this term and this term. The F1 term is already known to us as g cos theta, because of which it is flowing. So, with this we can now write the equation that we need to solve, appearing in this form. So, you can see that we have taken the mu and rho to the other side, multiply with the g cos theta, and so we have got this. So, we can see that the integration can be done once, and the way we have chosen the coordinates is such that the wall is at x is equal to delta and the gas is at x is equal to 0. So, that is very convenient, because when we integrate once and see the integration constant C1, then the first boundary condition for the gas liquid interface would set that constant to be 0. So, which means that the form of the velocity is going to be very simple. So, when we integrate a second time, then we can see that it comes to x2 square by 2, and then from a integration constant C2 we have, and we need to substitute the boundary condition at the stationary wall, u1 is equal to 0 at x2 is equal to delta, and that will give you the value of C2. So, what we do is that this value we then substitute into this, and therefore, we get the variation of the velocity as a function of x2. So, u1 as a function of x2 is given here, and we have intentionally taken delta as a common term, so that we can see the functional form with 2 parts of it. The first part is actually problem specific, and the second part is basically the profile. Okay. And what would be the maximum velocity? Maximum velocity should be on the top surface, and you could see that when you set x2 is equal to 0, you get the maximum velocity, and that is given here. Okay. And once the maximum velocity is given, we put the maximum velocity here, and therefore, we can do the scaling, which means that what is the velocity scaled with the maximum velocity, that is giving you the profile. So, the profile is then coming out neatly, and that's basically you can recognize with the square term that it must be a parabola. Okay. So, we have a parabola coming out as a solution for fluid flow when you have got this kind of a boundary condition. So, earlier problem, the trivial case we looked at, it was a straight line, but here we have got a parabola. And once you have got the velocity distribution, so you have basically got the velocity as a function of the distance. So, you could then from there use the Newton's law to write, for example, dou u1 by dou x2, and that should give you the tau. Okay. So, that is what actually is used here, and you can substitute and get the expression for the shear stress also. So, once you have these functional forms, then you can plot, okay, plot and see how they vary, and also see whether they are meaningful. So, when we plot, it looks like this. The parabola has a shifted edge bit. So, this is how the velocity profile should look like, and here I have drawn the parabola in a flipped direction intentionally to show you the nature as a parabola, and you can see only half of the parabola is actually applicable, and the slope here is 0 when you look at here in this direction. So, dou u by dou x2 is 0, okay, and the slope here will have some value, that means that the shear stress at the x2 is equal to delta, which is basically here on this side, will have some value. So, here the shear stress is 0 and here the shear stress has some value, and the maximum velocity is here, and the velocity at the interface between the wall and the liquid at this location will be 0. So, you could actually see that the parabola and the straight line are evident, and we now again look at the definition of shear stress and see what we meant by the shear stress being negative or positive. So, you could see that at x2 is equal to delta, which basically is at the wall. Okay. We are saying that the tau is negative. Okay. Now, what does it mean? Okay. So, it means that here we say that this is tau and this is a negative value. So, you are actually having x2 this way and tau this way. So, it has a negative value, and what does it mean by saying that it is negative? So, you could see that when we apply the definition, we see that the wall is exerting stress in the minus x1 direction. Okay. So, the minus has come here, okay, because the wall is trying to prevent the liquid from flowing. The liquid is trying to flow this way and wall is trying to prevent, and the way the x2 direction is in this way. Okay. So, which means that what is the layer at a higher value of x2, that is the wall. So, what is the layer at the lower value of x2, that is the liquid. So, the wall on the liquid is exerting the stress in the minus x direction. So, therefore, the shear stress should be negative. Okay. So, that is how it is actually given. So, in that sense this consistency is there with respect to the definition, and we could also then imagine that the stress at x is equal to 0 should be 0 here, okay, and that is also because you have got the slope of the parabolic profile also giving you 0 there, okay. So, because it is the maximum value of the velocity, which is also at the top surface. Okay. So, from here we then can derive some more quantities which are very useful in metallurgical problems, because we want to look at what would be the average velocity, what is the volumetric flow rate of the liquid slag or liquid metal over that inclined plane, and what is the mass flow rate, etc. So, very often these flow rates are available, and then we are then required to find out the average velocity, the time duration spent on the plane, and the oxygen pickup and so on. So, the average velocity is always defined in this manner. So, we have any functional form, if you have, then you have the ratio of the integrations. So, the numerator will have the velocity, the denominator will not have it, rest of them should cover the entire domain. So, in this case the domain is 1D, so therefore, there is only one distance variable. So, in the case of cylindrical coordinate system, which we will do in the next session, we will see that we will have differentiation that is done twice because of the way area is defined. So, you will have two dx's coming up here, dr and d theta. In this case of simple rectangular coordinate system, you have only one dx that is coming here. So, you then substitute the u1 as a function of x2, substitute and then perform the integration, and you would see that it would come out to be a ratio which is basically 2/3 of the maximum. Okay. So, it is very interesting to note that for a parabola, okay, in a rectangular coordinate system or rectangular coordinate system problems, you will see that whenever your the solution is parabola, then you would see that the average is 2 by 3 of max. Okay. So, this actually will be evident when we do more and more problems, and then it will also help us take a guess about the nature of the variations without even actually solving the problem. The volumetric flow rate is then available when we look at the cross sectional area through which the velocity is actually happening. So, the cross sectional area is this. So, you basically see that this is the height of the film, thickness of the film, of the liquid film, and this is the width. Okay, that is the z direction width of the plate. Okay. Through that area you have got the velocity that is happening, and therefore, volumetric flow rate is given by this expression, which you can then substitute and see that the delta is coming as a cube here. Okay. Here it is square, it is cube here, which means that when we substitute the values, we must be very careful, because often the thickness of the liquid layer is in millimeters, which when we see here is cubed. So, if we do not make the substitution correctly, then the volumetric flow rate can be quite off because of the cubic nature of the thickness of the film coming here. The mass flow rate is nothing but the volume flow rate times the density. So, you can see that here density times the volume flow rate, and therefore, if you see the expression, you will have density square coming and the thickness cube coming. So, here the thickness is generally in mm, and the density in SI units with the kg per meter cube will generally be in the order of 10 to the power of 3, okay, kg per meter cube. So, you can see that there is a large number that is coming here in rho, and there is generally a small number that is coming in the cube. So, which means that while we substitute numbers for these expressions, we must pay attention to the units and do not make any mistakes, because otherwise the values that we get for the m dot could be quite off. Okay. So, we have also in metallurgy other expressions that are of importance for us. So, we are often required to find out what is the average time spent by the liquid on the inclined plane. So, average time spent is basically the time taken for the liquid to go through the entire plane, and we take the average velocity and divide that below the length of the plane, then you get the average time. So, the length is available. Okay. So, the width is in the other direction, the z direction. So, this expression will give you the average time spent by the liquid, and if you substitute the velocity, average velocity expression, then you would get that. Okay. Now, the time of exposure to the ambient gas. So, the ambient atmosphere is a gas here, this is the liquid, and you have got the wall here. So, the time of exposure means that the liquid which is actually exposed here, and that is actually moving at the maximum velocity. Okay. So, the time of exposure calculation would require that we divide the length with the maximum velocity, and therefore, you have got a slightly different expression coming here. Okay. And that would be basically 2/3 of the average time that is spent. Okay, less than the average time spent. Okay. And when we substitute all the numbers, we must always ensure that the solution we obtained is valid. So, that is from the Reynolds number. So, we see that the Reynolds number as defined here can then be used to see that it is less than a critical number. So, this is the critical Reynolds number, and here in this problem it turns out to be 25. So, smaller better always. So, if you ensure that the numbers that you got are within this particular limit 25, then that means that the solution you got is reasonable. So, you could actually use those numbers as meaningful solutions out of the problem that we have. Okay. So, the other problem that we will look at is the flow between two plates. Here again the solution is not going to be different from what we have seen till now, but we want to see that the similarity nature, depending upon the term that we choose, the solution can still look very much similar. So, that is what we want to illustrate from this. So, here we have got two plates, and the two plates are stationary, and the liquid is flowing mainly because of the pressure gradient. Okay. So, here is the pressure gradient that is given. Okay. So, pH is the high pressure that is applied at this end, and PL is the low pressure that is present at the other end over the length L. So, Ph minus PL by L is basically the gradient in the pressure. You could see that the gradient is negative because it is decreasing with increasing x1, and which actually also means that when you apply higher pressure on the left hand side, the liquid should move in the right hand side, which means that U1 is actually in the +1 direction. That means the velocities are positive, and the y direction is x2. So, you are asking this. Okay. So, this is what we want to seek. Okay. So, the boundary conditions are given as follows. So, the velocity at the top wall and the bottom wall are both 0 because both are stationary walls, and from the no slip condition you have that 0. Now, we need to choose how to place our axes. So, the coordinate axes are placed in the center, so that the plus delta and minus delta will become the two walls. Okay. So, this you could say is at plus delta, and this will be at minus delta. So, there is a certain symmetry in this problem. We want to exploit that by simply also choosing the distances appropriately. It is not important when you plot it, but while deriving actually such simplifications make the algebra a little easier. Okay. So, again we go through this exercise of looking at the entire Navier-Stokes equation, and that is written for the 3 assumptions that we have written here, and making the simplification. So, we again assume that the pressure gradient is applied and the fluid flow is happening at steady state. So, we knock off this term because of the assumption 4, and we say the velocity is along x1. So, which means that u2 is equal to u3 is equal to 0. So, then I knock off this term and this term from the assumption 5. Okay. And then the velocity is varying only along x2. So, we do not have a variation along x3 direction. So, we then knock off this term also, and we say that the fluid flow is happening at fluid developed manner, which means that there is no gradient of the flow along the flow direction. So, which means that we knock off this term, and this term is actually second derivative of the same one. So, we knock that off also, and now we have got only 2 terms here, and we want to state that there is no body force term. Okay. So, which means that these are the only 2 terms that are coming of use, and of course, we also make an assumption that there is a pressure drop term is actually constant. So, we want to say that this is a constant because it could technically be a function of distance, but for our problem to be made simple, we want to take that as a constant. So, the differential equation will have only 2 terms, and that is what we have written here. Dou square u1 by dou x2 square is equal to minus delta p by mu l. Okay. So, now we can then integrate it twice to see that it would have x2 square by 2 coming up, x2, and then constant should be there. So, these are the integration constants. Okay. So, these constants are to be evaluated by using the boundary conditions. So, there are 2 boundary conditions that are available, and we substitute them, and we can immediately see that the solution will come quite symmetric, such that the velocity immediately can be seen as 0 at x2 is equal to plus delta as well as minus delta, and this is the functional form that we have sought. Okay. Now, we could see that again it is a parabola, and when we scale it, it also turns out to be similar to what we have seen earlier. Okay. Now, the maximum velocity is at x2 is equal to 0, which is at the center plane. So, which will give you the expression here, the pressure gradient times the del square by 2 mu. Okay. Now, when we divide the solution with the maximum velocity, we get the scaled velocity profile, and we see that the scaled velocity profile is actually giving you just the profile alone on the right hand side, which is a parabola. So, interestingly, the solution on the right hand side is identical to the previous solution, but the reason why the flow is happening is different. In the earlier situation it was a body force term. In this situation it is actually the pressure gradient term. So, they both have the same way of affecting the solution, and we also see that the earlier problem had half a parabola. Here you have a complete parabola. It is only a matter of the domain definition from 0 to delta versus minus delta to plus delta, otherwise the solution is identical. So, which means that some of the solutions, when we know, we could actually transfer them to new problems by looking at the similarities. Okay. The average velocity is calculated in the same way, and you would also see that the same relationship is coming here also, that is the average velocity to the maximum velocity has a ratio of 2:3. And we could also then apply the Newton's law to get the stress profile, and you could see that the stress profile comes as a linear function with a minus sign. So, similarly we can also see that it comes in this manner, and the stress profile will cross over the, it is 0, okay, okay, tau is equal to 0 at x2 is equal to 0, and you could see that it is at the center plane that the velocity has a maximum. So, here you would have the slope 0, okay, if you were to look at dou u by dou x2 at here is 0, okay. So, you would then see the stress is equal to 0. Now, you could also see that at the bottom layer then you have got a positive slope, okay, and you have got positive stress here, here I have a negative slope, you have got a negative stress value there, okay. So, you could actually see that you could predict the profile of stress profile from the velocity profile. You could also plug in the mathematical expression and arrive at the same thing, and you could also apply the definition here and convince yourself that the reason why the stress is given in this particular manner is actually valid. Okay. Now, the last problem we are actually not going to solve, we are only going to just combine the solutions from what we have done till now. Okay. Here is a situation where there are two walls, these walls are fairly long in the bidirection. So, the liquid that is in between the walls is getting mixed. The reason why it is getting mixed is because one wall is stationary, the other wall is actually moving vertically in the direction of plus y at a velocity v naught. So, this would mean that the flow is due to two reasons. Okay. So, earlier problems had the flow because of only one reason, but here it is because of two reasons. One reason is that there is a body force that is acting, which is in the minus y direction, this is minus g, okay, and the other reason is because of the wall being moved at a velocity v naught. So, these are the reasons why the fluid flow is happening. The boundary conditions are as follows: on the left wall you have got u1 is equal to 0, okay, because of the no slip condition. On the right wall you have got u2 is equal to v naught, again due to no slip condition. So, this problem we could actually see that if you look at the one combination, that is if you look at this and this, we saw that this must be a straight line solution, okay, and when we saw this and this together, we saw that it should be a parabola, okay. So, which means that we can predict already what the solution should look like, and we would actually do the same exercise, and we see that the equation is written for them, and we knock off the terms in the same way. So, that is because of the velocity being in only x direction, whereas variation along x2, which means that I remove this fully developed flow, then I remove this term, and then there is no pressure drop. So, I remove this term. So, you have got only this term and this term, okay, and this is already available as minus g there. So, that will get substituted. So, you can actually then integrate it twice. So, this is the solution, and when you integrate it twice you get two constants of integration c1 and c2, and these can be evaluated using the boundary conditions. X1 is equal to 0, you have got u2 is equal to 0, at x1 is equal to b, the right hand side wall which is moving at velocity v naught in the plus y direction. So, that would be here. So, then you can actually arrive at the integration constant. So, this will give you the velocity profile, and so u2 as a function of x1 is then available. So, this, as you can see, it has the parabolic term that is coming here and the linear term that is coming here. So, you can already see that from our analysis just a slide behind, we can see that it must be a mixture of a parabola and a straight line, and that is how it looks like. So, when you plot it would, the profile would look like that, okay. So, that the velocity in the left part of the domain would look going down, okay, and the on the right hand part you see that it should go up and reaching the velocity exactly v naught on the wall, okay. So, you could see that fairly down, you know. So, this is a plane over which the velocity profile is actually shifting, going down on the left hand side and up on the right hand side, which means that very far below, if you had a closed wall, so then the liquid has to mix, okay, it has to take a turn, okay. So, you could see that this kind of a arrangement would actually make the liquid mix up, which is actually the principle that is used in apple juice mixers or orange juice mixers that are available in the vending shops in daily life that you can notice, okay. So, here we will not solve this on the slide now, but I want you to try this out in your leisure. Where is the maximum velocity? You could evaluate it. So, you could actually check where is the slope going to 0 and find out the maximum velocity downwards, and then where does the flow direction reverse. So, you could also check at what value of x1 does that happen, okay, and so you could actually ask those things, and then you could see that you have got variability that is across V naught and B. So, by tuning V naught and B, you could then change these two conditions at your wish. Okay. So, we could actually go further by taking more and more terms, but at this moment we have already done enough to just check how the variation of velocity profile would come like. So, basically we are looking at solutions that are coming from only the diffusion term, okay, and only one at a time, and we are then getting the solutions in a simple form, and you can then see that the solution is applicable to the entire domain, okay, and this is something that we are going to relook whether this is reasonable or not later on, okay, but at this moment the diffusion profile is actually applicable to the entire domain, and that requires the laminar assumption to be valid, and that is the reason why we want to look at the critical Reynolds number, so that the solution is valid. And we are also going to then look at the reason why this is called the diffusion profile of velocity field. The reason is actually what is being diffused is the momentum. Okay, so, the momentum that is actually being dispersed within the medium because of the wall conditions are the reason why the viscosity is playing a role. So, these are all basically solutions for viscous liquids only, which luckily for us in metallurgical domain is applicable, because liquid metals and slags are generally very viscous. Okay. So, with that we close this session at this moment, and then we will have some numerical problems that will be made available to you as part of the course, which you can plug in and then check whether you are getting those numbers right. Some sample problems also will be available for you to practice.